مرحبا طلاب. I'll continue with the electromechanical system, which I ended up the last video with it. Before I derive the equations, I'll give you a brief description of a motor. So imagine you have a motor like that, something like that, with its parts and things, and imagine that you cut it like that. So if you cut it like that and you open, you will find this, you will see this, okay? So this part is the yoke, it's the part which is the solid, okay? On this part, you find that these are the poles, okay? On these poles, we have what you call the excitation or field winding. Field winding. This give what's called the flux or the IF, current of the field. Okay. Now look at this. They putting two poles. They come into pairs, so they give you the minimum number of poles here. It's one here and one here. Okay. Now you see the white part. The white part. All that it's open, it's an air, so it's empty. And this part is called the armature, or it's the rotor that goes round, okay? And on that armature, we have the armature conductor, okay? The armature conductor. Now in this, we can put to this the construction of this as a motor or generator is almost the same. But in the motor, I'll give it supply or تيار, IF and IA in here for the armature, and it will give me a rotation, okay? Either position, specific position, or to rotate in a specific speed, okay? So it give me, and if I use it as a generator, you will give it a movement in a prime mover, and it will give you generate electricity for you. That's why they say generating. So it generate electricity for you. Now from this, if I give this like this one, so I have تيار اللي هو IF or a flux. Then we'll have the equation. Remember that this will create a flux. You remember القاعدة that if I have like a flux عمودية على عندك هنا تيار وعندك flux عمودي، بدنا نقول if هاي كوندكتر عمودي على خطوط الفيض، فراح يسوي لي عندي هذا فورس. هاي الفورس راح تكون مثلا بهاي الاتجاه، نفس الشيء هاي راح تكون عندي بهاي الاتجاه مع طول الكوندكتورز اللي انا عندي. it will have a torque، فهذا it will rotate like that. Okay, let's say it's rotate like that. This is also we have a current carrying conductor here, a current carrying conductor همين عمودي على خطوط الفيض، راح يكون لي فولتية. تتذكرون انها تتناسب مع ثيتا دوت اللي هي السرعة، وبها طبعا شو اسمه الفلكس. remember this so that when I make you the schematic diagram and the block diagram, that you remember this is the simple instruction of a motor. Now let's come the schematic diagram, or a circuit diagram I call it. It's that one, okay? The difference here, we call it DC servo. What's the meaning of a DC servo? We either keep IF constant or we keep IA constant. We don't make them, both of them changing. So I'll give you the one which is armature control. This means that IF, that means the flux is constant, and IA or EA here is changing, which is coming from the other part of the control system. So this is from here to here, it's electrical circuit. And here, from here to here, it's mechanical. Okay, mechanical part. Now, this, if I manage to put this as this block diagram, then I can find the transfer function, which is theta على EA equal this one time this one time this one. So if you remember, على واحد زائدا هذا times هذا times هذا times هذا. So I'll find the transfer function. It will be something like this. So how can I start? Let's start. First we said that a torque will be developed. This torque is proportional to IA and IF. And because IF is constant, we say this is I'll give you back. We say IF is constant, the flux is constant. So if IF is constant, then we'll take a motor like, let's call it Km, it's a motor constant. So it's a motor torque constant, sometimes they call it K tau for the torque. And so this is the first equation which I get, that the torque equal IA تتناسب مع IA times IF, and it's equal to TA because IF is constant, so it's equal Km IA. Okay? When the motor is rotating, as we said, when the motor is rotating, we said that by generator action will develop a voltage. This voltage, high voltage, sorry, it's a bit high الفولتية تتناسب مع السرعة اللي دا يلف بها الموتور. So we can say that EB is a back EMF. EB equal KB times theta dot. This is another equation. Now, if you come to the armature, this is the armature circuit. How can you put the equation for this one? I say EA equal RA IA. If we say here is IA. Okay, so we say that EA equal IA RA plus L DIA by dt, and plus minus, because this is, if I take it, this is equal from the other side, minus EB. If I put this on the after the equality, so this is plus EB, or I say EA minus EB equal RAIA plus LA DIA by dt. So I have this equation. I hope it's clear. L DIA by dt زائدا RAIA زائدا EB equal EA. This is the armature circuit. IA armature circuit. Now what do we have? We have this mechanical part. This one we have. You remember we have a moment of inertia and we have a damping. So we have an equation. Armature produces C that governed by J theta double dot plus B theta. B is the damping, whatever the damping, maybe it's from the Bélier and from when it's moved from the air and all sorts. So it's equal to T, which is the torque, and equal to KMIA. This is, we'll use this later. واضح? So we started from here. We wrote the equation for the armature and the equation for the mechanical part and for the equation for EB and the equation for the torque, which is developed here. We can say that the torque is developed here. Okay? Now we have those four equations. Okay? Now we can put them into Laplace, because we construct the block diagram in Laplace, not in time domain. So we say T of S equal K, let's call it K motor, IA of S, this is equation 1, and EB equal KB S, because it was KB theta dot. In Laplace it will be KB S theta of S. This is equation 2. And from equation 3, which is the armature circuit, I just I rearrange it. I found IA equal 1 over LAS plus RA times EA minus EB. So I have EA from the, which is the supply to the motor, and I have this B, which act as a back EMF. Okay, this is equation 3, and I have theta of S equal 1 over J S square plus BS theta of S. So this is equation 4. Of course, you are, as a student, you can have, they are algebraic equation. You can have 1, 2, 3, and 4 equation. You can solve. We want to find the transfer function theta of S over EA of S. So the best way I find actually is to put it in the block diagram which I was talking to you about. Now listen here, I have E. After this I found here IA times K equal torque times this, it will be theta. and this is theta, this is EB, which we are talking about. Okay? Now, of course, the transfer function, it looks like a closed loop, that block diagram which I show you. Why it looks like a closed loop? Because of the feedback EMF. It looks like a closed loop. It's not a closed loop system, but it behaves like a closed loop. So theta over E of S, which is the transfer function, this means that you give it a voltage and you get a movement at the output, or you can get a speed if you like. We can change it. This equals G1, G2, G3 over 1 plus G1, G2, G3 times H. Of course, you know that G1 is equal to this one, and G2 equal to K of the torque, and G3 equal to that one, and H equal KB times S. So if we substitute for here, and it's one thing you have to remember, LA in this armature controlled DC servo is very small, so sometimes they ignore it. But for design, for practical use, for more accurate analysis, no, they don't ignore it. They leave it as it is. So here we have going to ignore it, and so substitute this into the G1, G2, G3 and the H, and rearrange it and ignore all the term that's multiplied by LA. We get something like that. Okay? It's something like that. So the transfer function is a second order of a second order system after the approximation. It's equal to K, a constant or a gain, over S, Tm S plus 1, and Tm يساوين time constant. Sometimes they put it K over S plus alpha, and alpha is 1 over Tm. You know that Tm is equal 1 over the roots, so it's the same. Where K equal Km over this, I'll give it here, and Tm equal Raj, it's the same denominator. It's the same denominator. K and Tm are motor gain and time constant of the system. And these parameter, or these Ra, the J, the B, the Km, the Kb are all characteristic of the motor. By choosing these parameters, you can choose the transfer function so that the motor will behave. But if you have a ready motor, so then these parameters of the motor are fixed. You can find them by other methods. Maybe you remember, I don't need it from you, but maybe you remember when we took it in control. If not, it's we are just looking for the simulation here, not the control. So it's not relevant in here. Okay. Because we are in a motor and we took about the state variable, so it's a chance for us to find the state variable state model of a servo motor. Okay, and so we go back. If you have the transfer function, you can find the state variable from the transfer function, you remember. But how we do it, we learn it's either by block diagram, the one I gave you in chapter 5, or if you go by MATLAB, you can find. But here, I'll show you how to find it from the equation. So I'll remind you that we have this equation, EB equal KB theta dot, EA equal LA DIA by DT plus RA IA EB. Okay. Now I have the third equation is torque is equal to K tau, IA tau. And we have the fourth equation, J theta double dot زائد MB theta dot equal to T. So now there are different approach. Sometimes they take theta as x1 and theta dot at x2. Sometimes they take x1 as omega, which is theta dot, which is the speed, and x2 is IA. So there are different approaches. Maybe I'll give you the other one as let's take the output as x1. So x1, if it's the output, That means the output is theta dot. That means the output is a speed in here. So it will be okay. I'll show you how to get the theta if you want from this model. So the first thing is substitute 3 here, that one, and this one, because you see here t. So this is like intermediate variable. Take it away. So substitute for t from here into here and rearrange it. How do you arrange it? You make theta double dot on the left side of the equation and all the rest to the right hand side of the equation. So substitute 3 and 4 and rearrange. We'll get this equation. Theta double dot equal minus b over j theta dot plus 1 over j t equal, and it's equal minus b over j theta dot plus k tau over j ia. So I substitute for t is equal to k tau ia, this one. Okay. Now substitute whatever relevant states. These are the state x1 and x2. So theta double dot it equal x1 dot. x1 dot is equal theta x1 dot, it equal the equation. So in a minus b over j theta dot is equal to x1 plus k tau over j ia equal x2. So this is in term of the state. So the equation, state equation, I remind you, is equal of the state derivative of a state and in term of the state and the input if you have the input. So here you find x1, x2 and the input, nothing else, no dot, no nothing, okay? And the parameter of the system. Now we have equation 1 and equation 2. So we have to substitute, take EB away and substitute is equal KB theta dot. So we'll have, I said substitute 1 into 2 and rearrange. Same thing here, I have a first order differential equation. So I'll say di by dt equal to minus RA LA IA plus KB over LA theta dot plus this KB comes to me from AB, which is in the equation of the armature, plus 1 over L EA. So I have to arrange this again in terms of this is x2 and this is x1, and I'll have a second equation that's in terms of a second state equation. Now, the last equation will be x2 dot equal kb over la x1 minus ra over la x2 plus 1 over la ea. I call the equation that I'm going to put into matrices as 1a, 2a. Okay, this one and the one before. Now put them into matrices. I'll have this form. I'll have x dot, this is x dot, equal minus b over j, k tau over j. In the equation maybe I use km, so it's okay, k tau over j, kb over la minus ra over la. This is x, of course, states, plus 1 and, no, this is 0. This is 0. I have no input in the first equation. 0 and 1 over la ea. The output we said is equal x1. So y equals 0, 1, 0, x. So y is equal x1. Now, if you use the formula, if I remind you, if you use the formula, this one, y over ea equals c si minus a inverse 1 times b. I don't have a d equal to 0. Then we get the transfer function omega s over ea اللي هي omega s هي theta dot. If you want to get theta of s over ea of s, the one which we derive, if you go here into Laplace, so omega of s equal s theta of s, right? So theta of s equal 1 over s omega of s. So I just multiply the transfer function which I get from here by 1 over s, I get this one. So theta of s over as, I can get it by this substitution. Okay, so this one you can get it after you use this one. After you use this formula, you'll get the one that is okay. Now sometimes I get some like a practical application. For example, sometimes I connect this, where do I use this motor? I connect this motor to something to do like something practical for me. If I go back, like let's say that I want to connect this motor to control the level of water in a tank. Maybe if you have taken other subject with me, I always mention this practical because I find it it's nice and easy, so the student will understand the practical part of sometimes I connect this motor like to open let's say a valve, and this valve will go into the tank, and so that I can control the level here H, and maybe I can put a reservoir so that anytime this water or any liquid